Thanks so much. Yeah, I'm very happy to be here. So I want to tell you today about Hurwitz spaces. And so Hurwitz spaces are one of the important moduli spaces in studying studying curves in algebraic geometry. So there's sort of two fundamental types of moduli spaces. In algebraic geometry for studying curves. And the first is the various forms of the moduli of curves. And so, and that just parameterizes curves themselves. And then the other kind is Hurwitz spaces. And Hurwitz spaces, they parameterize maps between curves. And so a lot of important information about these moduli spaces are contained inside their cohomology. And so we're interested in what we can say about the cohomology of these spaces. And so, for example, Harrer, around 1985, proved homological stability for the cohomology of MG, the moduli of curves. So namely, Harrer proved that the cohomology of MG, HI, stabilizes for I fixed what is it? For maybe G greater than or equal to 3I plus 1. Yes. No. And separately, it was proven by Madsen and Weiss in around 2006, 2007. They computed the stable homology. So they computed what exactly it stabilizes to. And so today I want to tell you about the second kind of moduli space, Hurwitz spaces, and basically analogous results in that setting. So in order to do so, I need to tell you what Hurwitz spaces are. So here's the setup that I want to use for Hurwitz spaces. So let G be a finite group. And C inside of G be a subset such that C is just a union of conjugacy classes. So I'll call the conjugacy classes C1 to CV. These are conjugacy classes in G. OK, so now given this data, there's a Hurwitz space there are Hurwitz spaces associated to it. So you can look at her G, C, and then there's some numbers, N1 to NV. And this is the following moduli space. So its points parameterize the following data. You have a G cover of the disk minus finitely many points. Such that the monodromy around each point is in C. And in fact, and Ni points have monodromy in Ci. So that's what these parameters are telling you. They're telling you how many points have monodromy in these specific conjugacy classes. And then there's an additional piece of data, which is you want a trivialization of the cover at a boundary point. Okay. So a point in the space pictorially looks like you have a disk. You remove some points. We write down a G cover such that when you look at the monodromy around these points, it's in one of these conjugacy classes, and this is how many are in conjugacy. I think this thing fell out. See if you can figure out how to get back on. This. Okay, hopefully that works. So those are Hurwitz spaces. So I guess these in particular are Hurwitz spaces over P1, so or A1. They're parametrizing maps to A1. And so those are the ones that I want to talk about today. And so, you know, there's also Hurwitz spaces, even though they're naturally they're objects in algebraic geometry. They're also very natural objects in homotopy theory. So there's a homotopy theoretic description of these Hurwitz, of the homotopy type of these Hurwitz spaces. So for example, you can say the following. So you can describe this homotopy equivalent to the following thing. You take the set of ordered tuples in C with ni elements in the conjugacy class Ci. And then I claim that there's an action of the braid group on this, the braid group on the sum of ni letters. And you take the homotopy quotient of this set, action of the braid group. And that's another description of the homotopy type of the Hurwitz spaces. And I need to tell you what the action of the braid group is. And it's the following thing. So if I have, it's determined by what happens on sort of simple positive braids. And so if I have a tuple x comma y, and I look at what a simple braided twist does on it, it gets sent to the pair x, y, x inverse, comma y. Okay. Sorry, did I mess up? Comma x. So that determines an action of the braid group, and then this is the homotopy quotient. So really, I mean, this space is just homotopy equivalent to the classifying space of a groupoid. And this is really, the homology of these Hurwitz spaces is really just some group homology. Okay, so there's a natural map from these Hurwitz spaces to a configuration space of points on a disk where the points are labeled by colors, and there are ni of each color. And what this map does is it just forgets the data of the C cover, and it just remembers the label around each point of which conjugacy class the monodromy was in. Okay. So, okay. Let's see if there's anything else I wanted to say. Okay, so there's some more structure on Hurwitz spaces. So you can take union of these Hurwitz spaces over all of the ni's, and when you do that, then the Hurwitz spaces form a topological monoid. They form an E1 algebra. This is an E1 algebra. And so you can multiply maps, and this corresponds to concatenation of covers. Okay. What else? Okay, so I guess I also need to introduce the connected Hurwitz spaces. So the connected Hurwitz space, it's just a collection of components inside the Hurwitz space, and namely, it's the one that corresponds to connected covers. So, it's just a union of components inside the Hurwitz space. consisting of connected covers. Okay. Are there any questions about definition of Hurwitz spaces? Sorry?
Is the thing that stops us from being an E2 algebra that there's a specific point in the boundary, or you know, but you don't know what it is?
So the thing that stops it from being an E2 algebra is actually this, it's this relation. So what this is sort of saying is that x, y is not equal to y times x. So x is like x gives you an element inside the Hurwitz space. It's just where you have a single puncture with monodromy x. Then you can look at x times y, and that's not the same as y times x. Rather, it's the conjugate of x, and of y by x. And so that's really the failure. So it's actually not so far from being an E2 algebra in spaces. And it is actually an E2 algebra in a slightly modified category of spaces. There's this category of G-crossed spaces. And from that point of view, the Hurwitz space can be described as the free E2 algebra in G-cross spaces. Like this union can be described as the free E2 algebra in G-cross spaces on the set C. Yeah, thanks for the question. Okay. So one way to think about it is you look at, so there are some tuples, and this condition that it be connected is the same as this tuple. The tuple should generate the group. Yeah. Okay. So in particular, we have stabilization maps that go as follows. So if you have some element x inside C, or maybe inside Ci, then what you can do is you can concatenate with the cover which only has monodromy x, and that gives you a map from GC n1 all the way up to nv to GC n1 all the way up to ni plus 1. And then, so it just increases, you're just sort of concatenating the cover, so you're increasing the amount of points with monodromy in Ci by 1. And so this is given by sort of concatenation with x, which I'll just call for simplicity. And so the main theorem I want to talk about today is that this map induces homological stability for connected Hurwitz spaces. So theorem. And so everything I'm talking about today is joint work with Aaron Lenzman. So the theorem is that in the setup of G and C, there exists AI, which are positive numbers, and then BI, such that this stabilization map induces an isomorphism from the homology of the connected Hurwitz space for G, C, n1 all the way up to nv. This multiplication by x induces an isomorphism to the next connected Hurwitz space. Okay. So this is for when you're in the stable range. So the stable range is for you want ni to be greater than ai times j plus bi. Okay. So there's some stable range for which this multiplication by x is an isomorphism on homology. Okay. So yes. So x is in Ci, and
There's only one I.
what do you mean? So I guess, sorry, yeah. So we chose some I, And then, yeah. Okay. Here's the eraser. So, okay. This result isn't completely out of the blue. So some cases of this result were known before, namely work of Ellenberg, Venkatesh, and Westerlund. They proved this result in the special case when G and C satisfies the non-splitting, what they call the non-splitting condition. And they didn't prove this exact result. They proved homological stability, I guess I should say, for Hurwitz space. When G and C satisfies what they call the non-splitting condition, and so I'll tell you what the non-splitting condition is. It's the following condition. You want that when you take this C and you intersect it with G prime, where G prime is any subgroup of D, you want this to be either empty or a single conjugacy class. For all subgroups G prime. So in particular, you're not allowed to have multiple conjugacy classes, and you need to stay a single conjugacy class or just not intersect for every subgroup, which either not intersect or stay a single conjugacy class. That's pretty restrictive. So for example, the most classical kinds of Hurwitz spaces are the Hurwitz spaces of simply branched covers. And so that's the example when G is the symmetric group on D letters, and C is the transpositions. So in this example, this satisfies the non-splitting condition only when D is equal to 3. And so beyond D equals 3, this result was not known. And in fact, Ellenberg, Venkatesh, and Westerlund, they conjectured that homological stability would be true for D greater than 3. Okay. So we don't just compute we don't just prove homological stability. We also say something about what the stable homology looks like. And namely, we say what happens when you stabilize in all the directions you can possibly stabilize. So with respect to all of the conjugates that are there. That's the next result. So you can state it as follows. So there's this comparison map between Hurwitz spaces and configuration spaces. And the statement is that when you're in the stable range, that map actually becomes an isomorphism on homology after inverting finitely many primes, namely the order of G, for example. So, and it's an isomorphism on each component of the source. So to state it, you have to choose a component, let's say, of the source. So we're going to choose a component inside the space that we're interested in, a connected component. And then the statement is that if Ni is greater than Ai plus Bi for all I, that was why I introduced I in the notation, then Aij, I guess. Then Hj of Z mapping onto Hj of this configuration space is an equivalence if you take coefficients in Z adjoin 1 over G. So in particular, it's true rational. Any questions about that? Yeah, so this is it's a multicolored configuration space. So this is configurations of ni points on the disk with label I guess. You have a bunch of points and then on a disk, and then ni of them are labeled I, and they're not ordered. And okay, so maybe what I'll say is we actually completely understand the homology of these configuration spaces, even integrally. So this is really a complete calculation of the stable homology after inverting in these directions, after inverting these primes, because we just completely understand this. Yeah. Yeah, exactly. Okay. And so for this result, I guess there's some history to that too. So Ellenberg, Venkatesh, and Westerlund, they tried to prove this result in this non-splitting case. But there was a serious error that was pointed out by Oscar. And Aaron and I were able to resolve that error in the non-splitting case. So we have a previous paper where we proved this result in the non-splitting case. Okay, so those are the main results. I want to tell you about, I'm not going to dwell on it too much, but I'll try to tell you about some of the applications. Yeah. It's worse. And I don't know what the optimal range is. It's bad. Okay, so I want to talk about some applications. So I'm going to focus on the applications to arithmetic statistics. So I want to mention two of them. One of them is their application to the Cohen-Lenstra-Martinet heuristic. And so I'll tell you what that is. So first, I'll say something about what the Cohen-Lenstra heuristics are. So the Cohen-Lenstra heuristics they predict the distribution of class groups of quadratic extensions of the rational numbers. And I really want to talk today about arithmetic statistics over function fields. So I'm not going to work over the rational numbers. I'm going to work over FQ join T. So P1 over, it's the function field for P1 over FQ. And so a quadratic extension of that corresponds to a hyperelliptic curve over FQ. So you can think of these as hyperelliptic curves. Okay, and so it predicts the distribution of what the class groups of these look like. And namely, here's an example of the kind of prediction it makes. So it says that if you choose a random hyperelliptic curve over FQ joint T, and you look at the probability that, let's say, the P part of its class group, so you take the class group of the ring of integers, and then you localize at P, and you look at the probability that that's isomorphic to a specific finite abelian P group. And so just to be clear, this is the ring of integers of the integers of a randomly chosen hyperelliptic curve. That is, I also want to assume it's ramified at infinity. Okay, so it predicts that this probability is inversely proportional to the size of the automorphism group of this finite abelian P group. And so there's a unique probability distribution on finite abelian P groups with this property that the probability is inversely proportional to the size of the automorphism group. And then the claim is that if you chose a random hyperelliptic curve ramified at infinity, that is what the distribution on its class group will look like. Okay? And so this is one of the main driving conjectures in arithmetic statistics. And so Ellenberg, Venkatesh, and Westerlund, they proved this. They proved a limiting version of this, so a weak form of this. If you take a limit as q approaches infinity. So this is a statement that you can make over for any finite field q, and they sort of took some limit as q approaches infinity, and they were able to prove this result by using exactly their homological stability result over there. And they used it exactly in the following case. So it's because, so the reason they were able to do this is because the point is that if you have the data of a hyperelliptic curve, and then a surjection from its class group onto this group H, this data you can interpret as an FQ point of a Hurwitz scheme. So there's a Hurwitz scheme, which is a scheme whose complex points are the Hurwitz spaces, but its FQ points exactly parameterize. In this particular case, they parameterize these things. So it's an FQ point of the connected Hurwitz space for this particular group, which is the semi-direct product of H with Z mod 2, and then the conjugacy classes order 2 elements. Okay, so using this fact and their homological stability result, so they were able to prove this covalence heuristics and some limiting. Yeah, so what you do is you take the distribution that you get by limiting, you look at discriminant less than or equal to some amount, and then you take the limiting distribution you get as you let that amount go to infinity. Is that? It's this, yeah, it's the same as looking at the degree, yeah. Okay. Sorry?
In the rational case,
yeah.
In the number theory case.
Yes. Yeah, so I mean, but you can make sense of discriminant for the function field setting, and it ends up just being the number of branch points. Yeah. And so, I mean, maybe I should say one more thing about how this is related, like why is this related to the cohomology of these Hurwitz spaces? And that happens via the Grothendieck-Lefschetz trace formula. The point is that the Grothendieck-Lifshitz trace formula tells you that FQ points on varieties are controlled by their étale cohomology, and maybe the Frobenius action on that étale cohomology. There are various comparison theorems that compare that étale cohomology to the étale cohomology over the complex numbers, which is just the singular cohomology. Okay, so they proved that, and then in our previous work, we used our stable homology computation to prove a more refined statement. So what we proved, we computed the expected number of projections from the class group of OK onto any H, so long as Q is sufficiently large. And so here we didn't have to take a limit as Q approaches infinity. We just needed to assume that Q is sufficiently large. And these expectations are the moments of this probability distribution. And so if you knew all of them for a fixed Q, then that would prove the whole probability distribution is what you think it is. Yeah, so if you prove this for all H for fixed Q, but unfortunately, we proved it for, if you fix an H, then we proved it for all Q sufficiently large, not the other way, yeah. So, okay. Let's see. Am I supposed to read that one first? So I guess I still didn't tell you what the Cohen-Lindstrom-Martinet heuristics are, which is what we do in this paper. So the point is that they kind of got lucky in Ellenberg, Vegetation, Westerlund. They got lucky because this particular group in this particular conjugacy class is an example of something that's non-splitting. And for more general versions of the Cohen-Lindstrom-Martinet heuristics, which is a generalization of the Cohen-Lindstrom heuristics, in general, they're just not non-splitting. And so we are able to prove, so we get results for the more general Cohen-Lindstrom-Martinet heuristics. And roughly the difference is that here we were looking at quadratic extensions in the class groups of those. In the Cohen-Lindstrom-Martinet heuristics, they're about class groups of gamma extensions for gamma is any finite group. So quadratic extensions are exactly Z mod 2 extensions. And so if you replace that with an arbitrary finite group, then they're more general heuristics as to what the class group how the class group should be distributed, and we're able to prove analogous results using these more general results. Okay, so that's the first application. The second application I want to talk about is Mahle's conjecture. So Mahle's conjecture. So Mahle's conjecture it's a more precise version of the inverse Galois problem. The inverse Galois problem asks, if I have some finite abelian group or some finite group, is it the Galois group of some finite extension of the rational numbers? And Mahle's conjecture goes beyond that. It says, not only does there exist one, but how many of them are there? And can I say asymptotically, in some sense, how many there are? And so, again, I'm working over function fields. So in this setting, it predicts the number of G extensions of FQ of this function field over P1 with down a discriminant. And there's a lot of subtleties in Mahle's conjecture, so the original conjecture is not correct, but there is there's sort of a modification for it due to Turkelly, in the case, which is correct in the case of function fields. And we established that for Q sufficiently large. So we establish Turkelly modification of Malus conjecture for Q sufficiently large. So the theorem, the following thing. So let G be a finite group. Then there exists some number A and B, and these are, I'm not going to define the numbers, but they're actually specific numbers. Like we have values that you can just understand in terms of G. And there's also some constant C such that for Q larger than C, maybe I should just say for Q sufficiently large, we have, maybe we also want Q to be coprime to the order of G. Then we can count the number of G extensions with discriminant less than or equal to X. Namely, we can say that asymptotically, okay, I should probably move it over here. So the claim is that the number of G extensions with discriminant less than or equal to X grows asymptotically like some power of X times some power of log of X. And so the precise statement is that if you look at the number of G extensions over FQ T with discriminant of the ring of integers less than or equal to X, then this number grows asymptotically, so it's upper and lower bounded by a constant times following function x to the 1 over a of g log of x to the b of g. And so maybe I should say that these are actually integers. Yeah, positive integers. Yeah. Okay. And so, yeah, that's this result. And again, it follows the same principle in the sense that these G extensions are parameterized by FQ points of certain Hurwitz spaces. Are there any questions about that? The next thing I'm going to talk about is the proof of homological stability. How much time do I have left? 20 minutes. That's probably enough. Yeah. Sorry, capital. Yeah. So the range will change what this Q sufficiently large means. It will tell you what Q sufficiently large means.
Isomorphism classes extension to Galois, right?
Yeah, so there are different ways you can do it. You can either ask for isomorphism classes, or you can talk about the groupoid cardinality of those things. And either way, this will be true, just because there are only finitely many automorphisms. And so this was only about asymptotic up to a finite number.
Does it matter if you say with a specified isomorphism Galois root to G or?
Oh no, yeah. See, I mean, I think that also shouldn't matter. Yeah, but maybe another thing to say is that actually in the number field setting, there is a conjecture about what the constant. There's like a, not only is it upper and lower bounded by a constant times this, it actually should converge to a specific constant times this times this function. But that's false in the function field setting. So this is kind of the best you can do. Okay. And so this result, there is sort of a weaker upper bound that was proven by Ellenberg, Tran, and Westerlund, but they had a non-optimal power of this B was sort of not optimized, and they didn't have the lower bound at all. Okay, so yeah, so now I want to talk about the proof of homological stability. So I'm not going to talk about the proof of stable homology because that computation was essentially already known given that homological stability happens. So the main using is that homological stability happens. So a lot of so the argument is largely inspired by what Ellenberg, Venkatesh, and Westerlund do, and also an article that Oscar Randall Williams wrote, which sort of explains Ellenberg, Venkatesh, Westerlund's argument and makes some modifications and simplifications to it. So what Ellenberg, Venkatesh, and Westerlund were able to show is that they showed that if H naught of the Hurwitz spaces stabilizes, then actually HI also stabilizes in some linear range, has homological stability. In some linear range. So they have some kind of formal argument, which in their paper, which shows that just assuming that you have what stability implies at the level of H naught, you actually get it for all of the higher homologies. And so one of the issues is that H naught of Hurwitz spaces don't have homological stability unless you have this non-splitting condition. So maybe for concreteness, what I'll do is I'll stick to the following example. So I'm going to take G to be the symmetric group on 4 letters, and C to be the transpositions. And so this is sort of the first case the first example of something that's not non-splitting. And in this case, what happens? So here's a sort of a reason why homological stability for the whole Hurwitz space doesn't happen, even though it does happen for the connected Hurwitz space. So you can look at the following elements. So this transposition, there's 6 transpositions inside the symmetric group. Let's call them x1 to x6. Maybe this is the transposition that's like 1, 2, and this is the transposition that's 3, 4. So you can consider the following element. You can consider x1 to the I times x6 to the j. And these elements for I plus j equals n, they form a collection of components inside the Hurwitz space, and they're all inside the Hurwitz space, the nth Hurwitz space. And so the fact that this family gets larger and larger as n increases, there are more and more ways to add 2 numbers to n. This shows that H naught doesn't stabilize. Because this family just gets larger and larger. Okay, so there's something, that was sort of the issue with this example, or these, basically all the examples where it's not non-splitting. Okay, so what do we do? How do you get around that? The idea is that instead of trying to first prove homological stability, you try to first prove something weaker. And in order to say what that is, I want to reinterpret what this argument is saying. So let's take, I'm just going to use her to refer to the union of all these Hurwitz spaces over n for this symmetric group and this conjugacy class. I'm just going to call it her to simplify the notation. And so one way to describe what their argument is saying is it's saying that if H naught of the Hurwitz space modulo the stability operator, there's some operator that induces the isomorphisms that make stability happen. If this is bounded, so this is some graded object because the Hurwitz space is graded by n, and this is some graded operator. And if this is bounded, then you have homological stability. And what's one way you can interpret homological stability? Well, one way to say what that is if you take the chains, the algebra of chains on the Hurwitz space, and then you mod out by this operator x, then this is bounded in some linear range of degrees. Because if this cofiber, so this really means the cofiber by the element x. So in this case, it's recording both the kernel and the co-kernel of multiplication by x. So if this is bounded, then what it's saying is that when you're outside that range, multiplication by x is an isomorphism, which is exactly what homological stability is saying. And so their argument is really saying that if you quotientize this one, so if you have this thing about h naught, then you really get this. And so what we do is we generalize their argument, and really the version of the argument due to Oscar to show the following thing. So we show that if you take h naught of this Hurwitz space, and you instead quotient by a sequence of elements. So in particular, the sequence that we're going to use is the sequence x1 squared all the way up to x6 squared. So what this means is we iteratively take the cofiber by each of these elements. And we show that if this is bounded, so what this really means is it's like a Koszul complex where you take this is some ring, and you take the Koszul complex where you quotient by all these elements, and you want that to be bounded. And we show that that implies actually that you have that the same thing is true for the whole Hurwitz space. So it implies that this is bounded in a linear range. Okay. So now, remember the statement of the theorem, which I was just, okay, that's the stable homology theorem. I guess I already raised it. So the statement of the theorem was that the connected Hurwitz spaces have homological stability. And so far, we're just looking at Hurwitz spaces. So the point is that knowing this result for Hurwitz spaces for all the possible Hurwitz spaces implies it for the connected Hurwitz spaces, because the Hurwitz space is built out of the connected Hurwitz spaces for various subgroups of G. So more precisely, you can write the Hurwitz space for this group S4. You can write this as, it has a filtration with associated graded, the Hurwitz space for various subgroups of S4, and you take the C and you intersect it with that subgroup. So G inside S4 are subgroups. And you can really set it up such that the ith associated graded piece this should be the connected Hurwitz space for the subgroup, where you go over all the subgroups where the size of the subgroup is I. So it's the union of these for the size of the subgroup equals I. Okay, so the point is that now knowing that we have this boundedness for this iterated quotient for all the subgroups means that we can use induction on the order of G and to learn that, in fact, if you take the connected Hurwitz space and you take its chains, and then you do this iterated quotient, this is bounded in a linear range. Okay, so this is not quite what we wanted. What we really wanted was just that when you quotient up by a single one of these elements, then it's bounded in a linear range. But here we're taking an iterated quotient by a bunch of things. And so one way to interpret what this is saying is that it's not really this is not a homological stability result. This roughly says that the homology of connected Hurwitz spaces grows as a polynomial. It grows asymptotically as a polynomial of degree less than or equal to 5. And so now the goal, so that's because, you know, if there's just one element, then that would be the same as homological stability, which is saying that it asymptotically grows like a constant. Like it asymptotically just looks like a constant. So really, quotient by 6 elements says that it's a polynomial of degree less than or equal to 5. And so what you now want to show is that, in fact, there was a polynomial of degree 0, namely constant. And so we're going to do that by sort of descending induction. And so what you can, so let me set up that induction somewhere there. So we'll choose some subset inside C. These are transpositions inside S4. So choose a subset of size I, and we'll prove by descending induction on I that that basically when you take the chains on the connected Hurwitz space and then you quotient out by the xi squareds, where the xi, or maybe I should call this something else, xj squared, where xj is inside the subset, we'll show that this is bounded in some linear range. So that's saying that you have the sort of homology grows as a polynomial of degree less than or equal to I minus 1. So this is what we want to prove inductively. So the point is the following. The point is that the inductive step is exactly a question that is a stable homology question in the following way. So you can choose some element that's not in the subset. And you can invert it. And so the point is that if you quotient by the square of some element that's not in the subset, we know that by induction, we know that that's bounded in a linear range. And so what that tells you is that any operator that's not inside the subset acts by an isomorphism in the stable range. And so in order to show that this was bounded in the linear range, we just have to show that that stable range is 0. So it's enough to show that if you take these quotients and then you invert all of the elements that weren't in the subset, so C minus S, let's write it like that, we need to show that this is 0. So this is saying that all of the operators that we're stabilizing it, and so once you get into the state, once you invert it, you're just looking at what was there in the stable range. And this is saying that whatever you see in the stable range was 0, so you already were bounded in a linear range. Okay, so there's some sort of reductions to some specific cases that are not so interesting. I want to focus on sort of a representative, interesting case of this. So let's look at the case when S is, or maybe let's look at the case when C minus S is the subset that is x4, x5, and x6. So I think I chose this one to be the transposition 3, 4. Let's choose this one to be the transposition 2, 3, and this to be 2, 4. And so this has the property that this is actually just S4. This is S3 intersected with C. So S3 is the subgroup where you're just permuting 2, 3, and 4. And so in general, the general case of this, really, the only interesting case is when this corresponds to intersecting C with a subgroup. And I just want to do this example for, I mean, there's nothing really special about it. Let's just do this for concreteness. So what are we trying? We're trying to prove that this is 0. So what do? Well, you observe that this thing that we're trying to study let's call this M. This really sits inside the chains on Hurwitz space, where you do the same thing. And it's sort of the top associated graded piece of the chains on the Hurwitz space. And so now the key thing is to consider this sort of comparison map to a smaller Hurwitz space. So I'll call this map G. So it goes to the chains on the Hurwitz space for the symmetric group on 3 letters now, for the same for C intersected with smaller subgroup, and you do exactly the same thing. So let me just remove this for a moment. That's OK. So let's give these names. Let's call this A, and let's call this B. And so the claim is that it's actually, so one claim is that if you take M and you tensor it along this map, then nothing actually happens. So M is just isomorphic to the base change along this map. So when you base change along this map, you exactly get, this is the same thing as the chains on the connected Hurwitz space, where you quotient by xj squared, okay, and S, but now you're working over the Hurwitz space for the symmetric group on 3 letters. And so the point is that if you can prove this claim, then you're done because, sorry, this is the Hurwitz space. Because the point is that this sits as an associated graded piece of the source. And this map is a filtered map, which on all the previous associated graded pieces, by induction, you can show as an isomorphism. And so on the top associated graded piece, it's also an isomorphism. But on the other hand, on this side, the top associated graded piece is just 0, because this is for a smaller group. And you don't see anything for groups larger than S3. And so that's just to say, this is the main thing that you have to prove. And so how do you show this? And so here the argument goes via descent. So you prove this via check descent. So there's this ideal sitting inside of the 0th homology of A, which is the ideal generated by x1, x2, and x3. And this ideal is exactly the kernel of the map G on H0. And moreover, this ideal acts nilpotently on this module M. And so what you want to show, so because it acts nilpotently on the homotopy groups or on this module, what that tells you is that it tells you that M is actually, you can write, so we're looking at this comparison map, and you can write these things as via their descent towers for the quotient by this ideal. So you can write this as the totalization of M tensored over A of A mod this ideal various tensor powers of this. And you can write this similarly as the totalization of M tensored over A of tensor powers of B mod this ideal, where you're taking this tensor power relative to A and relative to B. Okay? And so to show that this map is an equivalence, you really just need to show that each individual term in this cosimplicial object is an equivalence. And that amounts to just showing that when you take A mod I tensored bullet plus 1 over A, you need to show that that's the same as B mod I tensor powers of B mod I over B. And so for bullet equals 0, this is obvious because the ideal, like this map on H naught is surjective and the kernel is exactly I. And so this is just true. And so what's not clear is for I equals 2. So for bullet equals 1. So actually the general case just reduces to the case when star equals 1. And now the point is that this is something that you can model very explicitly at the level of spaces. And in fact, this is a key proposition in the previous paper that I mentioned, where we compute the stable homology in the non-splitting case. So the point is that the tools that we use in the non-splitting case to understand the stable homology, they're general enough to prove this result. And it's just some very explicit homotopy equivalence of spaces that you can write down. I'll stop there, maybe.
Suppose I know enough information about A and B for instance, also set of C and then
You know enough information about A and B?
so like E of A and B in your theorem.
Yeah.
For all subsets of C, will this allow me to say something about the group homological?
Can you repeat your question? Sorry. So
Know enough information of your constant of your in the will it allow me to say something about it?
do you mean the constants in the sense, like you mean where the stability range is?
Yeah,
Or,
or maybe anything.
So I guess it's telling you what the cohomology of the Hurwitz spaces in some stable range look like, and beyond that stable range, it doesn't really tell you much. When you say the group homology of the group, you mean G? Or, oh, I see. I don't know of any relationship to the group homology of G itself. One thing is that there's actually a G action on Hurwitz spaces given by conjugation. And another thing you can do is take the quotient by that G action. And so that's what's called the Hurwitz stack, and that parameterizes covers which don't have a trivialization at the boundary. And if you invert the order of G, then actually that doesn't change the stable homology. So our results also prove homological stability for that and stable homology for that. And for the Hurwitz stacks, where you take this extra quotient by G. And I guess that has a map to BG, so there's a map in from the group homology, but I don't know if it tells you anything. Yeah. Thanks. Yeah.
Feels like there's stuff going on in the background about the free loop space on BG and PHH.
Oh, definitely. Yeah, so one way to say it is the following. So if you look at BG, if you look at the free loop space of BG, in spaces, that's an E2 coalgebra. There's some interesting E2 coalgebra structure on that, coming from the fact that it's like the co-center of BG, I think, yeah. And then because of that, spaces with a map to loop space of BG have that category has an E2 monoidal structure, and these Hurwitz spaces are free E2 algebras in that category. That's one way you can describe this category of G cross spaces.
You mentioned how the homological case is heuristic related to FP points in the set, and then you can compute that by top homology. So in a number field case, is there any predictor about some
I'm not so sure. I talked once with Dan Peterson about this, and he mentioned some very conjectural things about like some infinite dimensional kind of cohomology theories in the number field setting that should conjecturally have the same kind of properties that are being used about étale cohomology. That would at least get you on the road to start talking about the same things. But as far as I know, yeah, I don't really know the relationship between the methods that people use in the number field setting and these.
All the questions.
Is it related to the final step where you mentioned how is it doing something integral or
Yeah. I mean, so the stability result happens completely integrally. It's really just the stable homology result that didn't. That involved inverting the order of group. So this result is really just, it happens at the level of homotopy equivalence of spaces.